Hi, everyone. I think we should start.
One question from the previous session. Until when we have to repeat the LMS algorithm because in each step it will be more precise, and but it may take too long to, for example, 50,000 repetition. It will be more precise, but it will take more time.
50,000 iterations for what?
For LMS algorithms.
For
Linear square method algorithms.
I don't think that will take that long time.
Really?
Yeah, you can try a bigger step size. Unless you use very small step size. Otherwise, I won't think you use 50,000 iterations or updates. You can try to increase the step size. Of course, if for example you're setting up the step size, you're seeing divergence. Obviously, your settings is too much, and you can decrease. But I suggest you to first try larger size rather than small. If you try to use like 10 to minus 8, well, yeah, it will take a long time. Okay, so first of all, maybe I've noticed in the canvas, the place for the office hour has been permanently changed to MEB 3105, and we have updated the change on our course website as well. Right? In case that you ignore it or you forgot the room number, you can just check out the course website. We apologize for that I don't know why, because in the recent few semesters, the department, the administration, constantly changed the locations for the office hours. I feel inconvenient as well. But anyway, if you decide to go to the office hour to avoid being confused or get lost, please check the website or the course website or the campus announcement first. Okay. Another thing is about homework 2. So we released homework 2 on last Tuesday, if I'm not wrong, right? So remember, homework 2 we only have like 14 days to finish, and we have a few practical tasks for you to implement, like least mean square method, like random forest, and ADA boosting, such kind of algorithms. I believe that you need to debug and spend quite a long time to get used to everything. So please start to do it early. Don't ask for attention don't ask for extension like 3 hours before deadline. That won't work. Okay. Okay, so let us continue with the Perceptron algorithm. So in the last lecture, we give a short start for the Perceptron, right? So basically, we're going to introduce first the details for Perceptron algorithm, and then we'll introduce the related theorem about perceptron. It's called Perceptron mystic bound, and we'll talk about, just like in decision tree, in practice, how do we implement several variants of perception to improve the robustness. Okay, so before we dive into the details of the perception algorithm, I would like to briefly review the setting for linear classifier, right? So in general, we assume that our input is an n-dimensional vector x, and the output is binary, so it's either -1 or +1, right? So here, for convenience, we usually choose -1, +1 setting. So, but in practical applications, you may say, okay, the label are 0 or 1. So in that case, please convert them into -1 and 1, right? So that you can directly apply the pseudocode in our slides. Otherwise, you need to make a corresponding justification, right? Adjustment, yeah. And then linear classifier, also called linear threshold units, classify an example using the following rule, right? So the following rule predicts the output using the sign of the classification function, right? So the classification function is an inner product between a weight vector and the input vector x plus a bias term b, right? So if we write it down, I mean, in element-wise, the way it is like this, right? So that means if this linear classification function is non-negative, we're going to predict the label to be 1, namely positive, right? Otherwise, we'll predict the label to be a -1, negative sample, and b is called bias term. So here are some graphical representation of linear classifier. You'll get used to that when we talk about artificial neural nets, right? Because in artificial neural nets, those one-layer classifier can all be represented by some units. This one is called a unit, which consists of the input units, where each input node represents one input feature. And between each input node and some intermediate node are edges, right? Each edge is associated with the corresponding weight. So feature weight W1 is associated with the input feature X1, W2, X2, W3, X3 until say this n-dimensional feature vector, so W8, X8, and finally we have a constant feature 1, which associated with the bias term. So then we connect them together to the intermediate node. That means, okay, I'm going to multiply the input from the node which coming in with the weight on the edge. So this W1, X1, W2, X2, W3, X3. And all those signals are integrated into this intermediate node by summation. That's what that means. That's what it means, right? And then then this output will be fed into the next unit, which is simply take the sign of this output. It just represents, okay, what is the sign of this linear combination of the weights and the input variables plus the bias term. Right? This is just a graphical representation for our linear classifier. Why this is interesting? Because when we say in artificial neural nets, most time we're going to preserve this part, but we usually change the top unit sign. We'll change it to some nonlinear activation function. Maybe you have heard them before, like sigma activation, like 10H, like ReLU, whatever. Okay. So, but anyway, we'll come back to it later in this semester. So for linear classifier, also have like a very nice looking geometry view, right? So our classification function determines a boundary, right? The boundary is actually the boundary which separates all the positive examples from negative examples. The boundary is described by the equality that the classification function, the linear classification function, be 0, right? So we know that, okay, the vector which is orthogonal to this classification boundary is represented by the classification weights, which is W1, W2, right? So I mentioned that before. Be careful. It's pretty straightforward to show this. Right? You can take any arbitrary 2 points here and subtract them, and then you do the inner product with this vector W vector. You end up with 0. So it's very easy to show that W1, W2 is perpendicular to this hyperplane or boundary, right? So then all the points on this side, that means their vector representations, the angle between their vector representations and this directional vector, W, is less than 90 degrees. So we'll predict those examples as positive. Right? Otherwise, all the points on the other side, right? So if you write down if you draw their vector representations, you say, okay, this is take this red point as example, right? Its vector is like this, right? So you can see the angle between this vector and this directional vector, W, is bigger than 90 degrees. And then that means, okay, you're going to predict them to be negative example. Okay? So this is the visualization result for like 2-dimensional, right? So for two-dimensional input space, our classification boundary is a line, right? For 3-dimensional, it is plane, right? It is plane, and for n-dimensional space, right? So it is called hyperplane, right? And the hyperplane separates the whole input space into 2 half spaces. So we're going to revisit this geometry representation of linear classifiers from time to time, because they're very important for you to understand more complex linear classifiers like supermax machines. It's very important. So now let us start with our boundary, right? The perceptron. Right? Perceptron was invented or proposed by this pioneer in artificial intelligence. His name is Rosenblatt, and it was originally published in Psychological Review. It's actually psychology literature. So the early AI development has close connection to psychology. And then again, it's just a funny thing. It shows that along with the development of artificial intelligence, there are always some hypes. Right? So the hypes at that time is no weaker than today's hypes. But what is the essence of perceptron algorithm, right? So it was first proposed by Rosenblatt in 1958, half a century ago. No, 1.5 century ago, right? And the goal of perceptron is not to build out some thinking machine. The goal is pretty straightforward. Is to find a separating hyperplane, linear hyperplane, to discriminate positive examples from negative examples. That's it, right? And the perceptron algorithm is an online algorithm. Namely, it just processes examples one by one. And later we'll see it is a very simple online algorithm, which is called the lazy online algorithm. And of course, in practice, we'll have several variants, and we'll discuss them briefly towards the end of this lecture. Right? So here's the algorithm details for perceptron. So our input for this algorithm is a sequence of training examples. We can view them as pairs of the input and output, right? So x1, y1, x2, y2, blah, blah, blah. So say, the algorithm requires that you feed the input in a streaming, in an online version, in an online fashion, right? So x1, y1, x2, y2, x3, y3, until say x and y. And we assume that every input vector belongs to an n-dimensional input space, and our output is binary, either -1 or +1. So to train a linear classifier with perceptron, right? So we first initialize the weight vector to be 0. So this is important. We need to initialize it as 0. Don't do the random initialization, okay? And then we just sequentially deal with each incoming example, xi or I, right? So we will first use our current weight vector, Wt, to make a prediction. So can we do that? We just calculate the inner product between the weight vector and the input vector. Oh, by the way, here we have used the notation simplification. That means we folded the bias term into the weight vector. Right? And also we augment the input feature vector with a constant 1, so that we just use 1 inner product represent the classification function. We do not need to explicitly write down the bias term, right? So then we take a look at our prediction y prime. So if y prime is the same as the ground truth label yi, it means okay, I make a correct prediction on the current example. Then I do nothing. I just stay there. I do nothing. I only update my model when I make a mistake. So that means my prediction y prime is different from the ground truth yi, right? So how can I update it? I use this rule. So I update my current weight vector Wt by adding it to a constant r multiplying with yi xi. So r is also called learning rate. So here you just assume it is a positive constant, same as our stochastic gradient descent or gradient descent, right? And then we need to multiply the current input vector xi with its ground truth label yi, and then add it to the current weight vector Wt. So we obtain updated version Wt plus 1. This is the rule to make update. And then we'll look at the next example. Say xi plus 1 or I plus 1. And again, I first make a prediction with my current weight vector, say Wt plus 1, right? And if I'm wrong, I apply this rule again to make updates. Otherwise, I just skip that example and look at the next example. So we do it again and again until we have go through the whole data set for a designated number of times, or we have made the maximum number of the iterations, whatever, right, under some stopping criterion, and then we return the final weight vector. That's the whole algorithmic framework for perceptron. So any questions so far?
How is this related to the B-square, the LMS? Is pretty similar.
No, I don't think there's some there must be some relationship, but it's not. But they are for different tasks. So first, this is only for classification. This is not for regression. So the updating rule looks a bit similar, right? But they are different. Any other question regarding understanding the algorithmic steps for perception?
Can you just say one more time what that R of YIXI term?
R is just like the role of the learning rate or step size in gradient descent or stochastic gradient descent when we talk about least mean squares, as you just mentioned, right? It's just a small positive constant. And later we'll say we just simply set R to be 1. Doesn't matter, right? But the things matter is the product xi multiplying with yi. Right? This is not gradient. It's just the input vector xi multiplying with its ground truth label yi. And we add this product, of course, multiply with R, scale with R, to the current weight vector to finish the update.
We just remember or remind me what the input vector xi contains. Is it a bunch of zeros and ones or negative ones and ones, or is it?
So xi can be arbitrary, can be continuous feature values, binary feature values, whatever. But here, remember, now that we use this single inner product to finish the classification function, right? So that means, okay, xi has some augmented feature 1 to fold the bias into the weight vector. This is something you should pay attention to. And I have a question because this is important. Although this algorithm is really straightforward, but I want to make sure everybody is on the same page. Okay, great. Again, for some algorithm, it's mathematically easier to represent false as minus 1 and at other times as 0. So if it turns out your task you define your binary label as 0 and 1, how do you modify the algorithm? I suppose your task, your boss asks you to use 0 and 1 to denote the positive label, negative and positive labels. How do you modify your perceptron algorithm?
So to look at the sign, you could look if it was greater or less than 1/2 on your predictions.
Yeah, on the prediction, yeah. But the issue is that how can we modify the update rule, right? If you insisted on that negative label must be 0, that means, okay, if you make wrong prediction on negative label, you actually won't make any update, right? So how do you modify this algorithm accordingly? We need to address that issue. And any suggestion?
You can just change zeros to -1 in the training examples and then run the algorithm.
Yes, the most straightforward, right? So, I mean, directly we can say y is 0, 0, 1 here, right? So just replace y by 2y minus 1. So you can see if y is 1, 2y minus 1 is still 1, right? If y is 0, 2y minus 1 is minus 1. So it's a very commonly used trick. So not only apply in perceptron, actually apply in many binary classification problems. People just turn binary yi to be 2y minus 1 so that you can switch it to be minus 1 or 1. Okay? So now let us look at why we should perform this update, right? So what's the meaning? I mean, why it is useful to update your weight in this way when you make a mistake, right? So we can classify the cases that are mistakes into 2 cases, right? First, if our ground truth label is positive and our classification is wrong, then what is yi? Y is simply 1, right? If your ground truth is positive, I mean y is simply 1, then when we update the perceptron rule, we actually directly add WT by R times xi, right? Because y is 1. Another case is that we make a wrong prediction for negative examples, right? So that means yi is simply minus 1. Then we will apply this rule. You actually subtract WT by R xi. So what's the meaning for this, right? Why when we under different types of mistakes, when we update our weight vector in this way and in this way, can improve our model or even correct our mistake. This is something we should be clear. We should be clear, right? So again, R is learning rate, a small positive number, less than 1, but for our subsequent analysis, I'm going to simply set R to be 1. And from the whole algorithmic framework, we can see that the perceptron algorithm is essentially a mistake-driven algorithm, because the updates are only performed on errors. If you make a correct predictions on examples, you never need to update the model. Right? You only update the models when you make wrong predictions. So this is the simplest version, and later we'll see more robust version. Right? So before we talk about the rationale of this update, this mistake-driven update, we need to first be aware. Actually, any type of mistake can be written as this inequality. So WT is your current weight vector. So if you make a wrong mistake, no matter in predicting positive examples or negative examples, you're going to have this inequality hold. Namely, the ground truth label Yi, W transpose Xi is less than or equal to 0. Why? Why my mistake can be summarized as this inequality?
Because the WTX term will be one sign and the Y term will be another sign.
Yes.
So if they're different, then you get a negative number.
Yeah, that's exactly right. So if you make wrong prediction, that means, okay, when Y is 1, then your prediction must be another sign, right? That means it has another sign. So Y is 1, then this inner product, your classification function must be negative. Y is negative, then your classification function must be positive, right? So their product must be negative. So that means, okay, we can conveniently use this inequality to test whether we have made a wrong prediction. So now let us talk about the intuition behind the update. So why doing such kind of mistake-driven update is good, right? So suppose we now have made a mistake on positive example. Right? That means the ground truth label Y is 1, and my prediction, my classification function, is less than 0. Then, according to our rule, our new weight vector is obtained by adding the current weight vector WT with the current input vector X. So here we set R to be 1. So what's the effect after we do such kind of update? We can take a look, right? After the update, well, what happened? Right? What happened to our classification? Right? So if we use the updated weight vector to make the prediction again, right? So we're going to compute the inner product between WT plus 1 and the input vector X, right? From which we just made a mistake. We found that because WT plus 1 equals to WT plus X, right? This is copied from the updated rule we have just done, right? And do the X, and then multiply with X, and then multiply X individually with each two terms, right? In the parentheses, we have like WT transpose X plus X transpose X, right? So now we can see that because X transpose X is non-negative, right? So that means after I update my weight vector in this way, my classification function essentially got increased, right? Upon the previous classification function. Why is this reason?
Because from geometric point of view, you just rotate the weight vector or equivalently the classifier towards the sample that we have labeled wrong.
Yeah, you're right. Yeah, but let us just from a simpler viewpoint. Later we'll discuss the geometry view, right? So from a simpler viewpoint, we can just check why we made a wrong prediction. Right? So why we make a wrong prediction? Because the original label is 1, right? The ground truth label is 1, but our prediction is less than 0. What does it mean? It means that you make a prediction because you make a wrong prediction because your classification function is too small, right? It's so small, it's below 0, so you make a wrong prediction. Now I use my perceptron rule to update my bit vector. You see, after the update, my classification function is increased, right? Because the classification function value is x transpose x more than the original classification function, right? The previous classification function value, right? So they got increased. So now you see that we actually improve toward the right direction, right? Our previous classification function value is too small, it's below 0, so I make wrong prediction for this positive example. So if I want to update my bit vector, I should ensure that after the update, the classification function value is increased, right? So that we can expect that the updated bit function value, the updated classification function value can somehow exceed 0, so we can correct our mistake. Does it make sense? Right?
Yeah, but you have to make sure that your updates do not change the previously correctly labeled sample.
Yeah, that's another story. Yeah, we'll talk about it. Later we'll talk about like mistake found theorem. We'll talk about how many. We'll talk about yeah, it is possible. But in general, if your data is linearly separable, we can always guarantee you find a separating hyperplane. Right? But anyway, for this particular example, right, mistakenly classified example, performing such kind of updating rule is reasonable, right? To summarize, right, for a positive example, the perceptron update will increase the score assigned to the same input. Right? So this is reasonable, right? So we can think about another case, right? If I make a wrong prediction for the negative example, what happened? It decreased value, right? If I make a wrong prediction, say y is the ground truth y is supposed to be -1, right? And you make wrong prediction, that means your classification function value is bigger than 0. It's too large, right? And now your update will subtract wt by x. That means after the update, your classification function value, so now we switch the positive sign by the -2 sign here, right? And you're gonna subtract the previous classification function value by a positive value. So actually decrease the classification function value. You're also improving your model in the right direction, right? Because you're gonna decrease the classification function value, right? Of course, we do not guarantee that just one decrease will let you to be right below 0 so that you can correct mistake. But you can imagine that if I make this mistake again, I keep decreasing until I classify, until I successfully classify this negative example. Right? So now let us look at the geometry of the perceptron update. Right? So suppose this is our old bit vector before we perform any update, right? So now we have a positive example x, right? Positive example x is labeled as +1. Right? So now we see that because this positive label resides on the other side, right? So the angle between x and WO is bigger than 90 degrees. So you're gonna predict this x to be negative. That means we make a mistake, right? And then how do you update? We're following this rule, right? Mistake on positive, we're gonna add the current weight vector to a constant r multiplying with xi. R is positive constant, right? So here we take r equals to 1, so we add w to x to update w. And now let's see, if we do this, how do we change the classification boundary, right? So if we add w to x, that means from geometry view, we're gonna make a parallel. The x will move it in parallel to here, right? We move the end of this vector x to the beginning of the x to the end of the direction vector w, right? So then we just connect the start of x and end of x, right? So get this addition, vector addition, right? So this is our new weight vector. And correspondingly, the hyperplane, the line here, who is orthogonal to this w mu is our classification boundary. So now, what's the prediction for this positive example again, based on w mu?
If the angle is less than 90%.
Yeah. So see the angle between the input vector and our weight vector w is now less than 90 degrees, right? So that means, okay, I'm gonna predict this example x to be positive. So you can see, actually we have corrected our mistake, right? So after one update, we correctly predict this positive example. Right? Of course, this is just like special case, right? So you can imagine if x is very, very small, and then probably it is not significant enough to rotate your hyperplane to this degree, right? So it's still gonna make a mistake. But anyway, it moves the classification boundary and the weight vector in the right direction, right? So you can imagine after several such kind of updates, you're gonna fully correct your mistake. Right? Any questions so far? Okay. So now let us look at the another case, right? What if we make a wrong prediction on negative example? So again, this is our current weight vector and the classification boundary. Right? Now suppose I have a negative example here. So the label is -1. So because the weight vector and the input vector, their angle is less than 90 degrees, right? So that means, okay, I'm going to predict this x to be positive. So I'll give a positive label. So obviously, I make a mistake on this negative sum. Then what should I do? We just read the rule here, right? So when we make a mistake on negative example, we're going to subtract the current weight vector by the current input vector, xi. Suppose we set r to be 1, right? So that means, okay, we're going to subtract w by x, right? That means we need to first find the vector which represents minus x, right? So what's that vector? You just switch the end and the start and end, right? So this is minus x. And again, is equal to add w to minus x, vector addition, right? So vector addition. So I'm gonna move minus x such that its starting coincides with the ending point of w, right? And then we just connect the starting of w and end of minus x. I end up with my new weight vector, right? So if we take a look at new weight vector, it points out points to this direction. So my classification boundary, which is perpendicular, is looking like this, right? So now, what is the classification result on X with this new weight factor? Negative, right? Because obviously now the input vector and the weight vector, their angle is bigger than half pi, right? Or 90 degrees. This is another example showing that how after this perceptron update, we can correct the previously misclassified example, right? So now I have learned why perception update rule should be like that, right? What's the rationality under that, right? So here we want to briefly discuss about the learnability of perception. So obviously, perception is learning a linear classifier model. So it's a linear classifier. So it cannot learn what it cannot represent, right? So it can only learn linearly separable functions, right? So if the functions are not linearly separable, obviously perception won't be able to give you a satisfactory result, right? And Minsky and Peppert in 1969 wrote an influential book that demonstrates perception's representational limitations. So the background is like that. Because of the hype mentioned before, right? When people develop the perception algorithm, there are many outsiders believe that artificial intelligence is approaching to human beings, and then this guy and another guy wrote a book and tell us it's not possible, right? Why? Because parity functions cannot be learned. XOR function. We actually mentioned that before, right? So actually, parity function cannot be learned by any linear classifier. But nowadays we know by performing some nonlinear feature transformation trick, and then try to find a classification boundary or hyperplane in a high-dimensional feature space will help us to address this problem. Any questions so far? Everyone is comfortable? Okay. So now I have introduced the perception algorithm details, the geometry of the update, why it is rational, and what can it represent, right? So actually, up to now, you should be able to implement your own perception algorithm.
What's the stopping criteria for perceptron algorithm? For example, in each update, your labels will be changed, and you have to make sure all of them are correctly labeled.
Yeah, for the stopping criteria, in practice, you can choose the maximum number of updates. Or you can choose if there are no mistakes. Like if you haven't gone through the entire data set, for one set you do not find any mistake, then you can stop. In that kind of case, if your algorithm stops at that case, that means okay, your data set is linear separable. You have already found a separating hyperplane. Right? But as we're going to discuss, actually, in many cases, the data set is not linearly separable. And then perception won't guarantee a stop unless you enforce it to stop. It enters into an infinite loop. So you must specify a maximum number of updates. Okay. Okay. So next we're going to talk about the properties of the perception, right? As some of you have mentioned, right? It's kind of too simple, and this updates might be totally local, right? It's just trying to correct the current mistaken classified example, right? So how about it influences other examples which was correctly classified, but now after update it is it was a mistaken classified. How can we deal with that? Is there any guarantee on that? So we'll talk about perception mistake bound and tell you in what kind of cases we can ignore such kind of mistakes. In what other cases we cannot. So the main conclusions include two theorems. So first is called convergence theorem. What is convergence theorem? It says that if there exists a set of weights that are consistent with the data, that means the data is totally linearly separable, we can always find out a separating hyperplane which perfectly separates all the positive examples from all the negative examples. Then the perception algorithm will always converge. It will always give you a separating hyperplane. Your training classifier, your training error is simple 0. So don't need to worry about like what if I update, make a correct update this time, but influence the update, influence the classification result for the previous example. You don't need to worry about it. As long as your data is linear separable, it always gives you a perfect separating hyperplane. Another conclusion is called cycling theorem. So what is cycling theorem? If the training data, unfortunately, is not linearly separate, then our perception will never stop, and eventually, if we make it update, right? So eventually, it will enter into an infinite loop. It will repeat the same set of weights again and again. Just like you have enter into an infinite loop such that you have a set of weights, you switch to weight 1, weight vector 1 to weight vector 2, weight vector 2 to weight vector 3, and after a few iterations, you're gonna go back to weight vector 1. So you'll do it again and again, unless you stop that. Any question? Okay, nice. Because it looks like you guys all feel this is very simple, right? Or comfortable, because my previous experience, I have a lot of discussion on the algorithm part and the intuition part, but it looks like you don't have any problems on it. Okay. So before we before we discuss those theorems, we need to introduce a very important concept called margin. Right? So this margin is not only used for perception. We're going to use it's a very important concept for you to understand fallback machine. So the margin, when we define margin for a hyperplane data set, that means okay, the margin can be defined for a data set only, and it also can be defined for a pair of a hyperplane data set. So let us first define the margin for a hyperplane and a data set. It means that the distance between the hyperplane and the data point nearest to it. So suppose we have this set of label examples, right? Positive and negative examples, and we have a separating hyperplane. Then the margin of this separating hyperplane with respect to this data set is the distance between the data point which is nearest in this data set to this hyperplane. So here it's just this positive example here, right? This is the definition of margin. But obviously, if your hyperplane does not separate your data set, it does not have margin for this data set. So be clear here, be aware. So when we talk about margin of a hyperplane, it must separate the hyperplane. It must separate data set. It cannot, if it does not, there's no margin.
I looked at training data set that's really large, but then the third piece of data, whatever, isn't like linearly separable from the first two. Does it just sit and loop on the third one, and you don't never see the rest of them?
Are you talking about perception?
Yeah.
No, there's no guarantee on that. I can only tell you, okay, it enters into an infinite loop, but in this inside this infinite loop, which read vector is gonna misclassify the boundary example or other examples are now determined. It depends on different data sets. Okay, so any question regarding the definition of margin? And we can further generalize the concept of margin to be the margin of a data set. So what is margin for a data set? The margin for a data set is obtained by, you just look for all possible separating hyperplanes. Each separating hyperplane has its own margin, right? So the one who has the largest margin is the margin for this data set. So like, again, this is 2 data set, right? So I have this separating hyperplane, I have this separating hyperplane, and this separating hyperplane. You see, we have like infinite many separating hyperplane, right? Each separating hyperplane has its own margin, and they pick up the maximum margin. This is called margin of the data set. So now I want to ask you to think about it. Right? So what does margin of a data set reflect? What does a margin of a data set imply or reflect the property of this data set?
The distance between positive and negative vectors.
Yeah, that's kind of this is a kind of distance between positive and negative. And any more general conclusion on that?
Well, a larger margin would mean that there's a clear distinction between positive examples and negative examples, right?
Yes, exactly right. So actually, just a step forward from your conclusion, right? So the margin of data set reflects, in general, how far away from the positive instances, between the positive instances and the negative instances, right? So obviously, the larger the margin, the easier for you to distinguish between the positive and negative examples. In other words, the easier for you to construct a linear classifier for that, right? So actually, margin reflects how easily you can linearly separable the data set. We'll jump back to this intuition again. We'll talk about the generalization capability of different linear classifiers. So now, because we define margin, right? Margin is regarding distance, right? We need to know how we define the distance, right? So, in terms of geometry, right? So, suppose we have a general hyperplane. Right? The hyperplane is represented as an equation, a linear equation. W transpose x plus b equals to 0, right? And then, according to some mathematical knowledge we have learned long time ago, right? I don't know when you guys learned this. I learned this in my high school. I almost forgot how to derive it. But anyway, for any input x0, I mean the point in the input space, the distance between x0 and this hyperplane is calculated by this. So we just substitute x0 for x is left-hand side, right? So just calculate this linear function and take absolute value. Obviously, we have to take absolute value. We need to ensure the distance is always non-negative, right? And then we divide the norm of the unit vector W. Then we get distance between x0 and h, right? The distance means that, okay, I just find a line to go through x0 and also perpendicular to the line, right? And just calculate the segment, the length of the segment. So the length of that segment is this. And then, because we will introduce the perceptron algorithm, mainly in the augmented feature space, right? So we'll talk everything we have already folded the weight, the bias parameter into the weight vector. That means we put b inside w, right? And also augment x with 1, right? So That means in augmented feature space, our hyperplane is simply this way, W transpose x0. Now we'll apply this formula. We can turn that in augmented feature space, any point, the distance between any point at x0 and this hyperplane is simply the inner product between W and x0, take absolute value, divided by the width, the norm of W. So imagine that if we're talking about a separating hyperplane, that means okay, I have a set of training examples, positive and negative example, and our hyperplane H can correctly predict every training example. Then we do not necessarily to write down absolute value. Right? We just write down this numerical as y0, the label of x0, multiplying with W transpose x0. Why? Why we can replace this absolute value of the inner product by multiplying with this inner product by the label y0?
They both have the same sign.
Yes, right? Because here we assume, okay, that will correctly predicts x0, right? The hyperplane correctly predicts x0, that means, okay, this value is always positive, right? If y0 is 1, then if you make correct prediction, your inner product must be positive, right? If y0 is negative, then your inner product must be negative as well, because you made correct prediction. So this is consistent with what we have just discussed, right? We can use inequality that this value is less than or equal to 0 to show that you make a wrong prediction, right? So now, I mean, with this definition in hand, right, we can talk about the a rigorous version of the mistake bound theorem. So let x1, y1, x2, y2 to until xm, ym be a sequence of training examples, and such that for every training instance I, right, the feature vector, which belongs to the n-dimensional space and have its norm less than or equal to R. So what does it mean? It just means, well, your input vector is kind of a normal vector, right? It doesn't contain any infinite value or negative infinite value. Right? Then your norm is actually the length of the vector, is upper bounded. Does it make sense? If any value in your input vector is a finite value, is bounded, then there must exist some upper bound, right, of the length of the whole vector. Does it make sense? It just means, okay, I assume that your training inputs are well preprocessed. There's no weird values in your input features.
When the number of training examples is finite, so always we have such R, it's the maximum of normal X size.
Yes. So there always exists such an upper bound R, right? And every label is, again, like -1, either -1 or +1. So the second condition is that suppose this data set is linearly separable, and then there exists a unit vector U. The unit vector U means that, okay, the norm of U is 1. Oh, by the way, what is the definition of norm? Don't confuse at this point. What is the definition of norm? Yeah, the square root of the square summation of each element in vector. It's just the just magnitude, yeah, or the length of the vector. Right? So don't be confused at here, right? We want to talk about less vector. If you feel like confused, look at think about the definition. No, okay. So suppose there exists a unit vector such that for some gamma, real value gamma, positive gamma, we have for every training example, gamma I, yi times u transpose xi is no less than gamma. So what does it mean?
Means all the samples have the same label plus one. Positive label.
Oh, no, it's not about positive. It just means, okay, first, this part, every yi times u transpose xi is now negative, right? So it means, okay, you can correctly classify all the training examples. But in addition to that, we require that this classification function value is no less than gamma. What does that mean? We can.
It has
You want
minimum distance to the.
Yes. I'm waiting for this. Okay, we can connect to our definition, right? So this is the definition of instance, right? So if our weight vector is unit vector, that means okay, the norm is 1, right? Norm is 1, and the numerator is just represented as this, right? So it's the same as here, right? So that means okay, for every training example, the distance between this training example and this separating hyperplane determined by u is no less than gamma. That means the margin is no less than gamma, right? Remember the definition of margin. The margin of a separating hyperplane for a data set is the minimum distance between the data points in the training set and this hyperplane, right? Any question? Okay, so given these two conditions, we can claim that the perceptron algorithm will make at most r over gamma squared mistakes on the training sequence. So r is the upper bound of the length of all the input vectors in your training data, right? And gamma is some margin. Is the margin for some separating hyperplane, right? Then I can claim that, okay, no matter how you run your perceptron algorithm, I just random perturbate or random permute your training sequence and feed them into perceptron. It will eventually result in a separating hyperplane, and the mistakes the perceptron made are at most r over gamma squared.
So does this mean you can stop the iterations of your algorithm after you make that many mistakes? Because
Yeah, of course. Actually, this is the upper bound.
Okay.
You can just count how many examples. You can just count how many distinct mistakes you have made, right? If you have made zero, you have go through entire data set, you have not made any mistakes, you can just stop. You even do not need to count this number. Any other question in understanding this theorem?
This is the number of mistakes that in each step perceptron can have, or at final step?
No, it just means if you do not intentionally stop your perceptron, you just let it run. And how many mistakes at most?
So it does not mean, for example, in the first update, you will have at most r over gamma, that quantity of numbers.
Oh no!
Mistakes.
Every update you just make one mistake, right? So only when you make a mistake, you make one update. It just tells you, okay, if you keep running perceptron, how many mistakes you're gonna make finally. That means after you make this many examples, you won't make any mistake. That means you can stop it because it's meaningless to run Perceptron anymore because it won't make any mistake in predicting your training example. You actually find a perfect separating hyperplane, right?
Can you just explain what R is again? Sorry, I missed it.
R is the maximum length of the input vectors in your training set.
So does that say then that like the number of mistakes is like proportional to?
It's not proportional. It's less than.
Sorry, related to. Well, what do you say then that the number of mistakes is then proportional to like the length of the vectors? Like the more features you have, the greater number of mistakes you have.
I won't say it's proportional. Again, I'm saying it's upper bound, right? It's less than or equal to R over gamma squared. Obviously, the property of this lower bound, of this upper bound, is proportional to R or proportional to, is proportional to 1 over gamma. But the actual number of mistakes can be much less than that.
So you could say that given a larger vector in a higher dimension, you could possibly make more and more mistakes.
Yes.
Okay.
I think that's a more strict way to discuss this result, right? So okay, so a few subtle things I need to emphasize. Right? So first, all the feature vectors are augmented with constant 1. So be careful. And second, as long as our features are normal, like does not contain weird values like infinity or negative infinity, we can always find out such an upper bound R, right? You can imagine like in an n-dimensional space, you have a ball which is large enough and cover all the training inputs, right?
Can you very quickly just say again one more time what that means that all features are augmented with 1? What you just said a second ago, you said all these features are augmented with +1.
It's not +1. It's you insert one extra feature, constant 1. So why we introduce that? Because in our classification, we just use this inner product, right? So remember, the definition of the classifier, linear classifier, is W transpose X plus a bias factor B, right?
Oh yeah, you fold it.
Yeah. Okay. So and again, what does this integrity mean, right? So it means that the data in U have a margin of gamma because the left-hand side part actually represents the distance between between each input example xi, yi, and the separating hyperplane U, right? So if the instance between every point and the hyperplane is no less than gamma, that means gamma is the margin. And someone asked why should we emphasize that? Why should we stress on that the vector must be unique, right? You can use any other vectors as well, but you need to modify the result correspondingly. Right? This is just for convenience. So if you hadn't been a unit vector, then we could skew gamma in the mistake bound. Then it will change the final mistake bound to the normal U times R over gamma squared. So say, what's the benefit? Why we should assume a unit vector U, right? Because we do not need to explicitly write down the normal U. So, but anyway, in addition to those details, right? What this mistake bound theorem delivers is that suppose we have a binary classification data set with n-dimensional inputs, if the data is linearly separable, and then the perceptron algorithm will eventually find a separating hyperplane after making a finite number of mistakes. I believe this is the most important conclusion, right? Although we say, okay, it's bounded by some value, but actually it says that, okay, anyway, you're gonna find a good separating hyperplane, right? As long as your data set is linearly separable. So now I want to go through the proof of this theorem. So from the proof of theorem, we can see how this bound is derived. So the setting of the proof. First, be aware, in our perceptron learning, we initialize weight vector to be all zeros. This is important. If you don't have this setting, it won't give you such a bound. And we simply set learning rate to be 1. You see that if we set any other learning rate, you will get similar kind of results, but let us just set learning rate to be 1. Right? And all the training examples are contained in a ball of size R. That's a way, maybe better way for you to understand why we put up such kind of constraint, right? So actually the R represents the span of your training set, the training inputs. And the training data is separable by a margin gamma using some unit vector U. So that means we have every training example x, y, I, y, I, we have this inequality. So now let's say with these preconditions, how do we prove that the upper bound of mistakes is this one? Right? So we actually have 3 steps in our proof. So first, we claim that after t mistakes, remember, for the perception, we only update when we make a mistake, right? So after t mistakes, that means we have updated our weight vector for t times. So we denote our weight vector by wt. So we claim that the inner product between the unit separating hyperplane u and our current weight vector is no less than t times gamma. So again, I just want to remind you that gamma is the margin of u, right? For the data set. T is the number of mistakes we have made so far, right? So how can we show this, right? Question is, how can we show this? And suppose we have after make t mistakes, let us use induction to do this, right? So then to obtain wt plus 1, according to updating rule, right? Wt plus 1 equals to Wt plus Yi xi. This is a perception update rule. So we can multiply u with this updated Wt plus 1. So which is Wt plus Yi times u transpose xi, right? You just multiply, you just replace Wt plus 1 by this. So you're gonna have like u transpose Wt plus Yi, u transpose xi, right? Remember, because for each xi and yi, the distance between xi and the separating hyperplane determined by u is no less than gamma, right? So we can apply the inequality here. So we have the W transpose Wt plus 1 is no less than u transpose Wt plus gamma. So this inequality comes from here, right? So just apply it here. Because the data is separable by a margin gamma, we can simply say, okay, this term is no less than gamma. So obtain that after making t mistakes, the inner product between u and updated weight vector is no less than u transpose Wt plus gamma, right? So we have show the first step of induction, right? So now look at the initial step. So in the initial step, we have W0 equals to 0, right? At the very beginning, our weight vector is 0. That means, okay, u transpose W0 is 0. So obviously, in the very first step, after you make first mistake, you have u transpose Wt is no less than gamma, right? That's t equals to 1. And now for arbitrary step t, as long as you have u transpose Wt is no less than this, then if you make mistake again, you have u transpose Wt plus 1 is no less than t plus 1 gamma, right? So this is standard induction. Then we can claim that after we make t mistakes, we have this inequality holds, right? Any question?
Case t is equal to 0, it means after 0 mistakes, you have something. So
No, t is 1. T starting from 0. T starting from 1.
but the starting of induction is 0.
It doesn't matter. If t is 0, then left hand side, right hand side, both 0, right? If t is 1, you have u transpose w1 is no less than gamma, right? Any question regarding this proof? So everyone is comfortable, right? So let me summarize. Briefly. Right? So, okay, my general conclusion is that when I run the perceptron, right? So after I make t mistakes, right? I can claim that the inner product between the unit vector u and the current bit vector is no less than t times this margin gamma, right? So I can prove that I use induction. So induction consists of 2 steps. The first step is the beginning. Right? We'll look at the very beginning whether this is satisfied, right? That means t equals to 1. T equals to 1. That means u transpose w1 is no less than gamma. Is it correct? The answer is yes. Why? Why? Because w0 is 0, right? So if you make the very first mistake, you're gonna add 0 with yi xi, right? And then you multiply, then you do the inner product with u transpose, with u transpose w0 is 0, and u transpose xi times yi is no less than gamma, right? So you have a immediate obtain that u transpose w1 is no less than gamma. This is the beginning case where t equals to 1, right? And then this is first step of the induction. The second step of induction is generalization, right? So that means, okay, for arbitrary t, I believe that, suppose this conclusion is right? So we need to check whether the conclusion for t plus 1 is also right. This is a generalization step. So we can show this from this infinity. If you still feel like confused, just watch the slides for 30 seconds and try to follow the proof. I don't think it's very difficult. Okay, looks like we don't have enough time to finish the proof today. But on Thursday we're gonna go through the details of this proof again, so that you won't feel uncomfortable.
Yeah.